Please make sure you have your copy of the assignment, Why Do Things Mix? What we'll do in this episode is look over the background for the experiment and the results, and we'll discuss some things to think about when answering the questions. There was a separate video demonstration that showed how the experiment was done and showed some of the other results that couldn't be performed in class. So you can watch that one before you watch this one. So the question, why do things mix? Well, it has to do with two rules of thumb. One rule of thumb, we say things mix because like dissolves like, and another rule of thumb, molecules stick to their own kind. Here's what that means. If you look at a mixture where molecules are able to mix together, they're mutually soluble with each other, both molecules attract to their own kind as well as they attract to the other kind of molecule. The molecules that are in this mixture don't see each other as different in terms of their polarity or their attractive forces, and so they're able to attract to the other molecule as well as they can attract to their own kind. But over here, where the molecules are mutually insoluble, how they don't mix is because one of the molecules attracts to its own kind more than it attracts to the other kind of molecule. There's something about their attractive forces or polarities that is different enough that one molecule just cannot attract to the other one as well as it can attract to its own. So one molecule attracts to its own kind more than to others. So the rules of thumb, molecules stick to their own kind. If they're different enough, they won't mix. Like dissolves like, that has to do with their polarity and their attractive forces. Things that have similar attractive forces, similar polarities, are able to dissolve in each other and mix. So the question is, what is it about the substances that we tested that makes some of them able to attract enough to each other and to themselves to stay mixed, and what is it that makes some of them unable to mix because they stick to their own kind more than to the other molecule? What we'll do is we'll go through the results and we'll look at the data, and when we're doing a discussion of the results, if you need to refer to the structures of the molecule, those are on the back of the first page. We'll go through the data that was collected in class and also on the demonstration video, and then we'll look at the questions. There are questions for the demonstration part of the experiment, for experiment number 1, which was performed in class, and for experiment number 2, which was performed in class. The demonstration that I'm going to do here might have some different visuals than are on your paper, but you can still follow along nonetheless if you need to look back at the structures of the molecules. Okay, let's look at the results. In the demonstration experiment, we found that water was not able to mix with oil, oleic acid, and it was not able to mix with butanol, but it did mix with butyric acid. Butanol, a large alcohol, was able to mix with oil and butyric acid, and butyric acid was able to mix with oleic acid or vegetable oil. So make sure that you have these results recorded on your copy of the assignment. In experiment 1, we were working with 3 different alcohols, methanol, propanol, and pentanol. We started by mixing those 3 together in a test tube, and we found that all 3 of the alcohols could mix together. No layers formed or separated. Then we took decane, which is lighter fluid, and water, and we combined those with the 3 alcohols to see if they would mix or not, and we also looked to see if the decane and the water would mix. We found that the decane was able to mix with pentanol and propanol, but not with methanol and not with water. Water was not able to mix with pentanol, but it could mix with propanol and it could mix with methanol. So make sure that you have a copy of these data in your copy of the assignment. In experiment 2, I demonstrated formaldehyde, and that was because it's a cancer-causing substance. Didn't want that at the lab benches. And what we found was that formaldehyde was able to mix with everything except for decane that we tested. Water was not able to mix with decane, but it mixed with everything else that we tested. Acetone was not able to mix with glycerin, and glycerin was not able to mix with decane. So using these results here, make sure that you record those on your copy of the assignment. Next, what we'll do is we'll look at the questions that go with each of the 3 parts of the experiment. Okay, let's look at the questions from the demonstration experiment. I'll start with question number 1. So the first question asks you to draw circles around groups of molecules that are mutually soluble. It's kind of like making a Venn diagram. So let's take those data. Let me find those data here. Where did I put those data? There we go. and we'll make circles around the ones that we're able to mix. So for example, water and butyric acid, those were able to mix. But water and butanol, they were not able to mix. Water and oil also did not mix. So I'll draw a circle around these two because they formed a group. They mixed together. Now butyric acid was able to mix with butanol right here. Butyric acid was also able to mix with oleic acid. So and butanol could mix with the oleic acid. So these three here, they form a group. They were all able to mix together. So the first step in each of these sets of questions will be to circle groups of molecules that are mutually soluble, the ones that could mix. Then what we want to figure out is why. What is it about their structures that makes that possible? Next, let's look at question number 2. Question number 2 asks about these 4 molecules, and it asks which of them are able to make hydrogen bonds. So if you look on your copy on the back of the first page for the structures of the molecules, I'll look at them here. I recopied them. So to find out if hydrogen bonding is possible, we look for the elements fluorine, oxygen, and nitrogen, and hydrogen. Hold the phone. So I see oxygen in all 4 of the molecules tested: water, butanol, butyric acid, and oleic acid. Wherever there's oxygen present would be a very strong negative charge in the molecule. So I'll put negative charges everywhere I see oxygens because it's the second most electronegative element on the periodic table. Now wherever the oxygen is attached to a hydrogen, the electrons are going to be pulled more towards the oxygen side of the bond, making hydrogen more positively charged. So everywhere there's a hydrogen, I'm going to draw the positive charge. All 4 of the molecules are able to make hydrogen bonds. And how you can tell is because they all have oxygen, and they also have oxygen bonded to hydrogen. Those are the things that you look for to tell if hydrogen bonding is possible. Next, let's look at question number 3. In question number 3, I just have parts of the molecules shown. The R here, that means the rest of the molecule. So the only part that I'm showing is the part that does the hydrogen bonding. I'm only showing the oxygens bonded to hydrogens wherever you find those in the molecules, or this oxygen here where those are found in the molecules. That's the only part that I'm showing. The rest of the molecule I'm not going to show. And the reason is because I just want to look at the parts of the molecules that are the same in all 4 molecules. So let's look at those parts. And the question is asking you to draw how water could attract to each of these molecules, the ends. So what you'll need to do is draw yourself some water molecules. And that's pretty easy to draw, just oxygen and 2 hydrogens. I'm going to label the charges here so that I can keep track of where the attractions are going to take place. And now I'm going to take my water molecules and I'm going to arrange them so that they attract by opposite charge attraction. So for example, I could put an oxygen attracting the hydrogen right there. That would be an example of a hydrogen bond. I'll put some dots there to show that opposite charge attraction. Now the same thing could happen over here in the same place because it's the same structure, oxygen bonded to hydrogen on both of these. So I'm going to put my hydrogen bonds here as well. Okay, so that's one example. And let me get another water molecule. And let me, I don't know, where else could I put one? I could put one right here. I could attract by hydrogen bonding this negative charge and that positive charge. And I can do that over here as well. Same thing, because it's the same structure, oxygen bonded to hydrogen. So I can do that all the way around that hydrogen there. Let me add another one. Okay, so right here I could have oxygen bonded to hydrogen. I can keep drawing water molecules all around both of these, like that. Let's get that oxygen in on the scene. So I could attract a water molecule right here because the positive charge of the hydrogen can attract like that. And I could do the same thing over here on this molecule. Let me turn that around like so. Okay, so I can get this in on here, one like that. I can attract the oxygen to the hydrogen. I can keep adding molecules going all the way around. Let me get one over here, like so. And I could do the same thing on this side over here, like this. So there are a lot of places where the water can attract But on this side over here, there's an extra place where I could have some more attraction. This oxygen can also attract additional water molecules that I couldn't attract before. Not on this side because I don't have that extra oxygen. So here I can attract another hydrogen on a water molecule. If I scooted this one over a little bit, maybe I could sneak another water molecule in there. So there's an extra opportunity for making hydrogen bonds in the other molecule, and that gives us a chance for additional hydrogen bonding. Let me add a little hydrogen bonding right there. Ooh, look, I can even do one right there between those two water molecules. Ooh, even over here too. There are a lot of places where hydrogen bonding could be going on between water molecules as well. But, okay, so anyway, when I look at this structure and this structure, there are more opportunities for hydrogen bonding in this one than there are in this one. So if I draw water molecules around them, I can draw more of them on this side because there's an extra oxygen that can attract more water molecules. Question number 4. Butanol and oleic acid. They both have an opportunity for hydrogen bonding. So that means that water can attract to both of these molecules. The same way that we were just drawing before. I could add a water molecule here. I could add a water molecule here. I could add one over here, and so on. I could keep on adding water molecules until I've gotten all the charges attracting. I can do that on this molecule over here as well. I can add some water and get them to attract where the opposite charges would attract. But the question is, if these things can attract to water, then why don't they mix with water? Why are they not able to stay together enough? Why do they separate to form layers? Well, the answer has to do with the next water molecules that you add. In order for these things to mix together, they need to attract to water molecules as well as they attract to their own kind. The water molecules need to be attracting to the butanol and the oleic acid as much as they're able to attract to other water molecules. But as I add more water molecules, you can see that they're not going to have much of an opportunity to attract to the butanol or to the oleic acid after this end is already attracting a few water molecules. It's like there's not enough space left for more water molecules to attract. The next water molecule to come along is looking for some hydrogen bonding potential, but there's none over here on this side of butanol. And the same thing with oleic acid. If I go all the way around this molecule, there's a big, huge end here. Does nothing for hydrogen bonding, only on this end over here. And since the water molecules aren't able to attract to the other side of butanol or oleic acid, the only thing they have left to attract to is other water molecules. And so I can find a whole lot of ways that these water molecules are going to attract to each other because they've got nothing else to attract to except each other. If molecules attract more to their own kind than to the other molecule, then they're going to separate into layers based on their difference in density. The lighter one is going to float and the heavier one is going to sink. So if the molecules can't attract to each other, if they can't attract to the other kind of molecule, then they'll just attract to each other and then they'll separate. So that's why they don't actually mix with water, even though they can attract, because they don't have enough opportunity to attract to the other molecule, enough that they're not just attracting to themselves. Remember those rules of thumb. Like dissolves like, and molecules stick to their own kind. If they stick more to their own kind, then they don't mix. Let's look at question number 5. Question 5 is looking at these two molecules, butyric acid and butanol. The water was able to mix with butyric acid, but not with butanol. But you know, they almost look exactly the same, don't they? They have 4 carbon atoms, the same straight chain. They have oxygen and hydrogen on the ends. The only difference is right here, that extra oxygen, which gives the strong negative charge wherever you find it, and the hydrogen bonding. The hydrogen has the strong positive charge. So why is water able to mix with this one but not with this one? If I put those water molecules around like we were doing before, I can attract those water molecules to the opposite charges and I can add them around like I did before. And remember that this oxygen here was able to attract some additional water molecules. in a way that down here we couldn't attract. We could attract fewer water molecules. So maybe that's the reason why water is able to mix with butyric acid, but not with the butanol, because the butanol only has this opportunity to make hydrogen bonds, the oxygen and the hydrogen. This additional oxygen is the only thing that's different between the two molecules. So that must be part of the explanation for why butyric acid can mix with water. It has more of an opportunity to attract water molecules. And remember, molecules stick to their own kind. If they can stick together as well as they can stick to the other molecule that's in the mixture, then they'll stay mixed. The butyric acid is able to attract to water molecules as well as water molecules are able to attract to each other. But here the butanol is not able to attract to the water molecules as well as water molecules attract to each other. There's less opportunity for attraction in butanol, more opportunity for attraction in butyric acid. Next, we'll look at the questions from experiment 1. We'll start with question 1. So the question is asking you to, again, draw circles around the groups of molecules that are able to mix together just like a Venn diagram. So I'm going to bring those data back over so we can see who is able to mix with who. Let me move that up a little bit. Okay, so according to our results, water was able to mix with methanol and propanol, not pentanol. So water was able to mix with this one and this one, but not this one, and water also did not mix with decane. So we can circle water, methanol, and propanol. Now on the opposite side, decane was able to mix with pentanol and propanol, but not with methanol or water. So I can draw another, this way right here, like so. Then the alcohols, the three alcohols, methanol, propanol, and pentanol, those three were able to mix. So we could draw a circle around those. So what is it about the alcohols that makes them all able to mix, but only the shorter ones, methanol and propanol, can mix with water, and the bigger one, pentanol, can mix with decane. Also propanol can mix with decane. Something about propanol seems to be right in the middle of the properties of water and decane. What could that be? Question 2 asks again, of the molecules that were tested, which can make hydrogen bonds. So I recopied those 5 molecules, the water, the 3 alcohols, and the decane, to see which ones can make hydrogen bonds. Remember what to look for? We look for oxygen. And I see oxygen here in the water, and in the methanol, and in the propanol, and in the pentanol, but not in the decane. Where the oxygen is found, there's also hydrogen present. So that means that will have a highly positive charge. And all three of the alcohols and water can make hydrogen bonds. Decane cannot. You can tell which ones can make hydrogen bonds because they have oxygen present or they have oxygen bonded to hydrogen. So that's the answer to question number 2. They all make hydrogen bonds except for decane. Question 3. So another thing we want to look for in the molecules is their dipole, if they have some amount of polarity caused by sidedness of charges. So looking at these elements, if you go back to the work that we did on our molecular modeling tutorial, oxygen has a higher electronegativity than hydrogen does, so that means that it pulls electrons more towards its side of the bond, giving it more of a negative charge, and the hydrogen more of a positive charge. Much the same is happening in the decane molecule. The carbon has a higher electronegativity than the hydrogen, so it's always pulling electrons towards its side of the bond. And that gives the carbon a little bit more of a negative charge and the hydrogens a little more of a positive charge wherever you find those two elements bonded together. So that means that all of these hydrogens can be labeled with a positive charge. Now this positive charge isn't as big a positive charge as you would have if the hydrogen were bonded to oxygen, nitrogen, or fluorine, as you find in the hydrogen bonding potential. So even though these are labeled as positive charges, water molecules don't attract to them because it's not as strong a positive charge as the positive charge would be over here in this water molecule, because the hydrogen is being attracted to oxygen, making a very polar covalent bond. All of these carbons then are going to be given a slight negative charge. And then what we want to look for is the sidedness or symmetry of the molecules. So, beginning with water, if I divide it down the middle this way to look for symmetry, there is definitely symmetry from side to side. There's mirror image sidedness in the water molecule from left to right. But if I divided it down the middle this way, from top to bottom, there's a definite difference in the sides. This side is more negative on the top, the bottom part is more positive, so we would say that this is a dipole, a polar molecule. If you do that with the decane, if you divide it down the middle this way, well, the two sides are mirror images of each other. They have the same number of carbons and hydrogens. So there's complete symmetry going this way. And if you divided it down the middle this way, maybe the same thing on the top and the bottom. So from top to bottom, there's also symmetry. There's total symmetry in the decane molecule. No matter which way you slice it down the middle, it always comes out mirror image sides. So this is a very non-polar molecule. There's a dipole in this polar molecule, water. There's only symmetry in the non-polar molecule, decane. Question 4. This one gets a little bit tricky. So question 4 is asking about is these three alcohols, methanol, propanol, and pentanol. And it says as they get longer, meaning the carbon chain, here's 1 carbon, 3 carbons, 5 carbons, as the molecules are getting longer, what happens to the way that they mix with the water and with the decane? So water is able to mix with methanol and with propanol, but water is not able to mix with pentanol and decane. So that means that there's something about the likeness of these molecules for water. These molecules are more like water than these molecules. That's why they're able to mix. So if you compare the molecules, if you go this way, which way are these going in terms of how much they're like water? So how much they're like water is increasing in this direction. As the molecules are getting shorter, they're more like water and more able to mix. Water is a polar molecule. Decane is a nonpolar molecule. The farther you go this way, the less they're able to mix with decane. As you go this way with the molecules, the more they're able to mix with decane. So the pentanol and propanol were able to mix with decane, but methanol and water couldn't. So there's another trend going this way. So what's happening as you go this way, as the molecules are getting shorter, they're more like water, and since they're more like water, they're able to mix with water. If water is a polar molecule, then that means that the shorter the molecules are, the more like polar water they are, the more polar they are. So more polar as you get longer. But as you get longer, the longer the molecules are, the less polar they are, the more like decane they are. So less polar equals longer. The longer the molecule is, the more it's like decane and able to mix with decane. The shorter the molecule is, the more it's like water and it's more able to mix with water. If it's more like water, it's more polar. If it's more like decane, it's more nonpolar or less polar. Now, what part of the molecule is making that happen? Well, if you look at the part of the molecule that shows that symmetry that we were just looking at, right here, there's that symmetry. Right here, there's that symmetry. If I divide it down the middle, top and bottom, it's the same left and right, top and bottom. It's the same and the same. But the amount of the molecule that shows that symmetry is increasing as the molecule gets longer. This symmetry is what gives this molecule its nonpolar nature. And the shorter it is, the less of that symmetry you find in the molecule. The longer it is, the more of the molecule shows that symmetry. So more symmetry, because it's a longer molecule, more symmetry equals lower polarity. More nonpolar as there's more symmetry. Look at the decane. It's the ultimate in symmetry in the molecules that we've been working with. So the more you're like decane, the more you're nonpolar, the more you're like water, the more you're polar. Last set of questions, let's look at experiment number 2. And we'll start with question number 1. And the question is asking us once again to draw circles around groups of molecules that can mix together. So let's look at those data and see who was able to mix and who was not. Starting with glycerin. Glycerin was able to mix with water, but it was not able to mix with formaldehyde. So I can make this group right here. Something about glycerin is very different from the other molecules, that it's not able to mix with them. How about water? Water was able to mix with formaldehyde and acetone, but not with decane. So I'll circle these: water, formaldehyde, and acetone. And let's see, formaldehyde was able to mix with acetone, but it was not able to mix with decane, so I can leave it in this group here. Acetone was able to mix with decane, so I can circle that right there. So there are 3 groups of molecules. There's something about these 2 molecules that's very different from these 2 molecules. And formaldehyde seems to form a bridge there. It seems to have some properties that straddle the water and the acetone, but not enough to mix with decane and not enough to mix with glycerin. So what is going on with those molecules? Well, let's look at the next part. Question 2. Which of the molecules can make hydrogen bonds? We've done this a couple times now, and we know what to look for. Look for oxygen. Wherever there's oxygen present, we can make hydrogen bonds. So we can do it here, and here, and here, and here. Oh, and look, there's a hydrogen there, so we can add a positive. And here, there's a negative and a hydrogen, so we can add a positive. Same thing here. Looks like glycerin's got a lot going on. And down here, decane, nothing. No oxygens anywhere, so we can't make any hydrogen bonds. So in answering question 2, which of the molecules can form hydrogen bonds? They all can, except for decane. And how you can tell? You look for oxygen. You look for oxygen bonded to hydrogen. In other molecules, we look for nitrogen or fluorine. But in these molecules, we just have oxygen. Question number 3. This diagram shows the formaldehyde molecule and the acetone molecule. Now those 2 are able to mix with each other, but they don't make hydrogen bonds with each other. The formaldehyde has a negatively charged oxygen here, but it doesn't have enough of a positive charge in its carbon atom here in order to make a hydrogen bond. Although the attraction is making that carbon a little positively charged, it's not as strong as you would find in a hydrogen bond. Carbon does have a higher electronegativity than hydrogen, so electrons are pulled more towards the carbon side of the bond compared to hydrogen. Carbon is a little bit more negative in that part of the bond. It's a little more positive compared to oxygen. Again, positive and negative are relative terms. It's like tall and short. Carbon is short compared to oxygen. It's tall compared to hydrogen. And there I'm using the charges to mean tall and short. Carbon is more negative compared to hydrogen, but it's more positive compared to oxygen. Down here in the acetone molecule, we again have that negative charge from the oxygen, but we don't have hydrogen bonding because this carbon here is not hydrogen. Now between the carbon atoms, since they have the same electronegativity, we don't draw any arrows. But because these carbons have a higher electronegativity than the hydrogens that they're attached to, those hydrogens will have a little bit of a positive charge, and the carbons will have a little bit of a negative charge right here. So how can these 2 molecules attract to each other? There is an opposite charge attraction because these molecules form a dipole. This molecule here is symmetrical down the middle. If I cut it in the middle, this one is also symmetrical down the middle, so there's no polarity from left to right. But from top to bottom, if I divided them this way, this one has a dipole with a negative charge and a positive charge, and so does this one. It has a dipole with a negative side where the oxygen is and a positive side where there's no oxygen. There's also a dipole. That's the attraction between these 2 molecules. It's called a dipole-dipole attraction. It's not as strong as hydrogen bonding, but it is an important attractive force between molecules. So I'm not going to draw the little green dots like I would draw for a hydrogen bond. I'm just going to show that those two are attracting. Opposite charge attraction. It's a dipole-dipole attraction. It's not as strong as hydrogen bonding, but it does allow these two molecules to attract to each other as well as they attract to their own kind. And that's why they're able to mix, because molecules stick to their own kind. Things that are alike in their polarity properties will dissolve in each other. Both of these are alike enough in their polarity to attract to each other as much as they attract to their own kind, and that's why they're able to mix. Question 4. This one is tricky. So if you can do this one, question 5 will be a piece of cake. Alright, so this question is asking about these molecules. It starts by saying that water is a polar molecule. And then it asks about formaldehyde and acetone, which one is more like water. So let's set up an imaginary line here where water is polar on one side, and I'm going to put its opposite, decane, over here on the other side. Polar because it has a dipole, and decane is nonpolar because it has complete symmetry, which we saw earlier in a different discussion. And so now the question is asking about these two molecules. Which one is more like water and therefore more polar? Well, both of them are able to mix with water. So in that sense, they're both like water. However, they were both not able to mix with decane. Only acetone was able to mix with decane. So between these two molecules, acetone is more like decane, and formaldehyde is more like water. Even though the formaldehyde and the acetone can mix together, because they're enough alike, the formaldehyde is more like water, and acetone is more like decane. These two are able to mix, these two are able to mix, these two are able to mix, but these could not. So that makes formaldehyde different from decane. And remember, the way that we are using our rules of thumb, like dissolves like. Things that are more alike in their polarity are able to mix together. Things that have similar attractive forces will stick to the other kind as much as they stick to their own kind. So if we were ranking their polarities, we would say that formaldehyde is more like water and less like the decane. So what part of the structure of the less polar molecule, this one right here, makes it less polar, and why? Well, if you were to just cover up this part of acetone and just imagine that it wasn't there, it looks a lot like decane. It looks more like decane than formaldehyde does. Formaldehyde has that same structure, but it's not as big. And like we saw earlier with the 3 alcohols, the longer the chain in the molecule, the longer the carbon chain, the less polar the molecule is. This one right here, the acetone, has a longer chain, so it's more like decane in its structure. It's less polar, or more nonpolar like decane. Formaldehyde, look at that. 2 hydrogens on either side. What's in the middle? There's an oxygen in the middle. It looks a lot like water, except it has that carbon there, but it's still very similar in its structure to the water molecule. Acetone is more similar in its structure to the decane molecule. It has that extra bit of symmetry. If you take away the carbon and the oxygen, it looks a lot like the structure of decane. So what makes the acetone more like decane is the length of its chain, its carbon chain, and the increased amount of the molecule that has the symmetry. Question number 5, the last question. This one is a very tricky question, and I'm not going to go the whole way through it with you because I want to see what you can do with it. The question is asking about glycerin and water, and which one is more polar. So to figure that out, you're going to have to look at how glycerin and water interact with the other molecules. And based on how they attract or not, you can figure out which way these two molecules are arranged in terms of polarity. So for example, these two molecules both do not mix with decane. Water and glycerin are not like decane. They're more polar than decane. But now the question is, if we were arranging them in order from more polar to less polar, would water come before glycerin, or would glycerin come before water? To figure that out, you've got to look at how these molecules mix or not with the other ones and analyze which ones are mutually soluble and which ones are not. Good luck with that question, and if you figure it out, bring me your answer to homeroom so we can discuss it.